So, then welcome. What is this? The 7th lecture in the Lattice Boltzmann methods in winter 23. So today we talk about some initial and boundary conditions. So in particular, we go look at our playground tool here. That is using Lattice Boltzmann. You can see you can of course put some, oops, I rather do it this way, yeah. So in a fluid simulation we somehow have to specify several things. For example, where we put stuff, that would be this thing here, and you see oops, I cannot move it now. What's happening? Yes, okay, I can move it. So here we apparently specify a wall, and here we specify some velocity. We can have a look on that, edit boundary conditions. So what we have here is velocity boundary conditions in the front. Also on top and also in the back. This is a little bit a strange way of doing things, but this is because this is a play, a toy more like a simulator. Here we could have, for example, at the top, could also have something like slip. Down here we have no slip. The no slip is the same thing as we have on the surface of our body here. We can also put slip here, then I'll have it kind of symmetric, yeah. So today we'll talk mainly about how we can implement some boundary conditions similar to these. Also, we may speak about initial conditions. I can set here initial conditions which are not consistent. This is why we have this transient. Yeah, I just reinitialize the flow field with a given velocity, and then you see it starts all over again. So then let's go to the lecture. It starts with, so there are 3 parts. First is related to scaling, and then we have initial conditions and then boundary conditions. So, okay, I'm a little bit handicapped with my pen today. I'll do my very best to make this work. So we start with scaling of units, and here maybe I'll go briefly back to the simulator to give some indication. So we have, of course, our problem with physical units, like this would here be 12 meters, yeah, and then 30 meters, and here is the velocity meters per second, right? So what we use in Lattice Boltzmann method, and what is somehow called the world, so these are called world coordinates in this tool here because they are related to the real world thing. But what we usually use in Lattice Boltzmann is so-called lattice units. So lattice units, yeah, so there's 12 meters as related to 12 grid nodes in this direction and 300 grid nodes in that direction, yeah, which in this tool we can also have some changes. For example, we can change the resolution. No, in delta x we can of course not change the resolution. We can only change the resolution in world coordinates. Then we have a resolution of 1 meter. Let's play it to see that this actually has some consequences. We go back here. So there's no distance here is 1 meter, so we can have, for example, higher resolution, like double the resolution, yeah. No, something something went wrong here. I don't know why it's doing this. Okay, there was obviously a mistake. I doubled the resolution and it became coarser. Yeah. So view. Now I went to 1/3. Yeah, a little bit less. So you see the simulation. We now have a higher resolution. We can go back to how many grid nodes we have. Now we have 400 by 1000 grid nodes, and of course what we observe is that the simulation now becomes much slower, yeah, because we have to update more grid nodes, obviously, yeah. Okay, and here also the velocity is now given in delta x by delta t. So let me pause this and go back to the lecture, because now we have, of course, the problem that we have to relate these things, grid spacings and distance and also time, with lattice units. So we'll say that there is given a delta x which comes in the units of meters, and there is given a delta t which comes in the units of seconds. And what is obviously required is a mapping between the delta x and the physical distance that it means. So so both ways, of course, from physical units, from physical velocity, u. So we call the physical stuff with a star, and say physical pressure P star to the lattice velocity u and lattice density in this case, because the pressure is related to the density, rho. By the way, the density in our play tool here is when we want to, no, not here, when we want to display it, it's a bit, so the guy was not a fluid mechanics guy writing this, yeah. D is here the density. I have to play it, so otherwise we don't see it, yeah, and it comes in delta x by the 1/3, or when we put it to world coordinates, it comes in kilogram per cubic meter, yeah, and this is how it looks like. So vortex here is a low density in the center, yeah. So this is a vortex. You see it if we turn it back to. So the best you see is when you look at the curl. Not defined what this is, but you see here's a vortex, and in the center of the vortex is always a low part of is the density or the pressure is low. Okay, let's actually do the lecture. Okay, so let's first look at the lattice velocity. Lattice velocity. So the lattice velocity u, of course, I mean, it's all the same thing. So it comes in delta x. We measure it in delta x by delta t. And usually, because we put this in the computer, we don't write in the computer delta x by delta t. We just take it as a number. Yeah. So delta x by delta t is in that sense implied when we talk about a velocity. The velocity, of course, is defined in 2 dimensions at least as the sum over I, or the vector I and j. In 3 dimensions it would be ij k, and this into Fij delta x by delta t, where this part here is often omitted in practice. So in that sense, the scaling works rather like this. We write this, so both of them are basically the same. We just have to replace the units, and what I'm going to do is I write here in red, no, not in that red. This was the same red, sorry. Delta x, delta t, sorry. Delta t by delta x into, okay, today I'm a little bit stupid, by delta x by delta t. So they are of course the same, yeah? We just eliminate them. And what we say is, so we are going to keep this as the units that we have, and we are going to replace this. So what I mean by this is, for example, we have to know, of course, what they are. So say delta x, for example, could be 1 millimeter. We just had it as 1 meter, but say it's much smaller. And delta t is 1 microsecond. And say the velocity that we are concerned with is 0.1 meter per second. Yeah. So what are we going to do? We say that our velocity u is our physical velocity 0.1 meters per second. Now we replace these things here, so I should have written them in red. Yeah, so this is 10 by the power of minus 6 seconds by 10 by the power of minus 3 meter, and we'll keep that here. And so this is 10 by the power of minus 3, and then there is 1 here, right? So we get up with 10 by the power of minus 4 delta x by delta t, okay? Yeah, not so difficult, yeah? Okay, good. So this is how we translate from physical units to lattice units. The pressure is something that we always requires some more discussion, because in the kinetic theory does not need a pressure. This is an invention of the Navier-Stokes guys. Yeah. So here we just have different moments. So the pressure in LBM is usually expressed, not usually, it is expressed by an equation of state. So this is something that the Navier-Stokes equation just ignores. So the Navier-Stokes equation says that there's pressure coming from somewhere, and here we have, of course, to specify where it's coming from. So the idea where we say it's coming from is P star is equal to rho times c, the speed of sound square, where the speed of sound square, I mean, what is this? This is the gas law, yeah, because this here is related to the gas constant times the temperature, yeah, and rho is the mass divided by the volume, right? So and you put this into it, so you get the gas law, yeah. So you get the pressure comes out of the gas law. Okay, then One thing, when we talk about the Navier-Stokes equation, there we only use relative pressure. This is, if you think about, by the way, this is from a practical perspective. When somebody starts implementing their Lattice Boltzmann code, and I've seen this through the last through the last 20 years, a lot of times students giving some exercise implementing this. The most common problem that they run into in the beginning is that they initialize their pressure, their density with 0, and are confused that this doesn't work. So in the Navier-Stokes equation, in the Navier-Stokes solver, you would probably specify pressure somewhere and you set the pressure to 0, right? Because the Navier-Stokes equation only cares about, so for the Navier-Stokes equation, pressure is a potential, and you set your base potential somewhere arbitrarily, and so it makes sense to say there's an outflow and here we put pressure 0, yeah? Just makes sense, because there's no other reason. Physically speaking, and then the Boltzmann equation is of course physical thing, yeah? If there is 0 pressure, then there is nothing, yeah? There would be vacuum, right? Yeah, you see this in the gas law. So in the Lattice Boltzmann method, you cannot just put 0 pressure, yeah? Because this you will then divide by 0. Okay. But what we have is a relation between pressure. So what is interesting for us is a pressure that we have divided by a base pressure, and this should be related to two densities. And I write the physical, on the left I write it in the physical way, and on the right I write it in Lattice Boltzmann units, because this ratio would be kept. Yeah. So but this P0 would be, so to speak, the surrounding pressure, the 100. What is it? What do we have? 1,000 hectopascal, 1 bar, right? Yeah, so atmospheric pressure, or if you are underwater, yeah, then the pressure that you have there, yeah. Okay. Now, still, what we can do and what we usually do in Lattice Boltzmann, rho 0 can be set to rho 0 equals to 1. So we basically say there is no mass. For example, when we go briefly back here, turning on our density and playing this a little bit. Okay, you see the density. Okay, we still, there's a small problem with the resolution here. I'm sorry for messing this up. 0.2. You see, the density, of course, comes in kilograms per cubic meter, but if we turn this to lattice units, it's just 1 divided by the volume, right? Okay, let's pause this here. Okay, so we can set, this basically means we set the mass to 1, so we ignore that there is mass, and what this means, we can state that rho just is being the pressure that we have compared to an atmospheric pressure P0. Yeah? Okay, let's just have an example. Yeah, considering, yeah, okay, So the typical problem that we have is a tube, yeah, where we have a pressure P1 here, which corresponds to rho 1 here. We may have a distance L, and so we have a pressure difference, yeah, P2 in this place, and we have a rho 2 in this place. So let's say the pressure difference in our example would be 100 Pascal, and the background, the atmospheric pressure, would be 10,000 hectopascal, which means it's 10 by the 5 Pascal. So rho 2, this is our outflow, say rho 2 is our rho 0, and our rho 0 is set to 1, though then rho 1 divided by rho 0 would be P star plus, no, sorry, delta P star plus P0, which is, of course, the difference. P star is, of course, the difference. And this divided by P star would give us a 1.00. So this is the way how you would put a pressure difference of 100 Pascal into lattice Boltzmann units. Okay, coming to initial conditions. Coming to initial conditions, which we in future will write as IC. So there's a difference between lattice Boltzmann and Navier-Stokes equation. So this is here important to understand that we need initial conditions for all moments, because all moments are degrees of freedom of our system, right? Yeah. The Navier-Stokes equation only requires initial conditions on the velocity and the pressure field. Now this is a problem for us, because we get initial conditions from someone, and you say, okay, this is my velocity, this is my pressure, now set initial conditions for your lattice Boltzmann scheme, and there is missing information. Yeah? So how do you fill the missing information? There are several ways of doing this. I'm not discussing all of them, but let me discuss two of them. So one is, which is often used, for example, also in our tool, or toy, whatever you want to call it, the equilibrium method. So let's say there is given a u of x at time 0 and a rho of x, the position, yeah, and 0. Then what you can do is you can just compute the local equilibrium distribution, which we've learned how to do it. Of u and of the given stuff. They come from the Maxwell moments, or more precisely, you should use the way of computing your equilibrium that you also use in the kernel. So we learned there are different ways of doing this. You can use the Taylor expanded equilibrium, or you can use the moment expanded, the moment matching. Yeah. So you'll compute them. and you set them, and then it starts, and then you will see that everything is fine. This is a simple method, and this method works. And this is also the reason why 90% of initial conditions, or more than that, most of the initial conditions in lattice Boltzmann are set this way. And usually this works because you're not very much interested in the initial conditions. However, there are these cases where sometimes you are interested in how the simulation actually starts, and you are interested in how long something takes to happen, for example. And in this case, you need accurate initial conditions. Yeah? And in this case, then it does not work because the second moments are now wrong if there are gradients in the initial condition. So with having gradients, I mean having gradients that are not zero. Yeah. So what would this mean if you do not initialize the second moments correctly? You got wrong dissipation, and this means you have the wrong start in your simulation. I mean, you can easily see in our toy, when you remember you start the simulation. Yeah, you start the simulation, and in the beginning, this is not necessarily accurate. Yeah, so I restart, and then you see pressure waves going everywhere. Yeah, so this is not a consistent initial condition. Okay, but it doesn't matter if you are just interested in later times. Yeah, then it will this thing will dissipate. So let's see, what would you do if you are interested in accurate initial conditions. So then you will have to set a second moment non-equilibrium initialization. And this second order non-initialization makes use of asymptotic analysis. So, what we want to do in principle, we want to solve the Navier-Stokes limit, and this requires the second order moments to be second order consistent in the smallness parameter epsilon. Yeah, the smallness parameter epsilon is here related to the grid spacing. And we require that third order moments are correct in equilibrium. So this is something that we've discussed now several times. So they need to be only they need to be first order consistent, and this is the same as saying we only need the equilibrium. So what does second order consistency mean? Looking at the asymptotic analysis that we had last time, and we know that M200 what am I doing? Okay, we need this to second order, it's not written here, is M20 equilibrium to second order minus 1 over omega minus 1/2. Here comes 2/3 dx ux, and this now to first order. Yeah, we are losing one order to the derivative, so to speak. Yeah, and this into rho to the zero order. Yeah, this would be the second order of this moment. Then the second order of the other moment, of course, looks the same. Second order is m0 to equilibrium second order minus 1 omega minus 1/2 here 2/3 dy uy first order rho into zero order, which is a constant. And then, of course, we have the moment m11 second order is equal to the equilibrium to second order minus 1/2 minus omega 1 over omega 1/2. Maybe I just write the 1/3 in front, and then we have here dx uy first order plus dy ux also to first order, and this into the zero order, the constant density. So the constant density is 1. The third order then be simpler. Here we have m21, which only, you see, this is confusing. It's the third order moment to first order. Yeah, third order moment to first order, and this is only 1/3 rho 0 ux to the first order of yeah, and this, sorry, I'm really a little bit handicapped with this tool here. This is equal to 1. No, sorry. I mean, I want to say this is the same as the equilibrium to first order as the equilibrium, because there's no derivative in it, right? Yeah. So, and you see, similar. This is the same thing for m21. First order is 1/3 rho 0 uy. First order is also m21 equilibrium to first order. I mean, this is the required minimum consistency. You can go higher consistency for your initial conditions, but this is what you require for solving the Navier-Stokes equation correctly. Yeah, so we'll need all the stuff in pre-collision. So suppose we start our simulation from a pre-collision state. So then we have to rewrite them. By the way, this is something that I expect you to be able to do in the exam, yeah, now because we have this overbar version, which is the average between pre and post collision, but we have to initialize with the pre-collision, yeah. So how is the pre-collision different? So of course, when we set initial conditions, we cannot set to a certain order. We just can't set the initial conditions, right? This is why I don't write an order here, yeah. So we set this to the equilibrium, which we can compute. And then we'll have, instead of 1 over omega minus 1/2, what will we have? We will have just 1 over omega rho 2/3 dx ux. So I will expect that you are able to see what you have here in 1 over omega, what is the difference between this overbar version and the non-overbar version. By the way, now I'm testing you. Suppose we would initialize with the post-collision, which we could also do. What would we have to write here instead of 1 over omega? If we have the average, we have 1 over omega minus 1/2. If we have the pre-collision, we have 1 over omega. So this is enough information from which you can already deduce, even without knowing it, what would be for the post-collision state?
Plus 1/2, 1 over omega.
1 order?
1 over omega plus 1/2.
No, not plus 1/2. No, 1. Not plus 1/2. 1 over omega minus 1.
Okay.
Yeah. So that's if you add the two together and you divide by 2, yeah, you'll end up with this. Yeah. Not plus minus 1. Okay. So let me just write this other thing down. We need this here, rho 2 third dy uy, and okay, the last guy m1. So you need to know from your initial condition what these derivatives are. Yeah. So if you have a function for your initial condition, of course you can compute these things. Or if you have no function, you may be able to compute them by finite differences. Okay, so this would be one way of putting initial conditions. There's also other ways of doing consistent initial condition. There is an iterative way of putting initial conditions by solving the Poisson equation, which I'm not discussing here because I've never used this method myself, and I also think it's probably not setting initial conditions. It's more like a preconditioner because you have to do iterations to get to your initial condition. Yeah. If you do it this way, you can set your initial condition directly, as you would usually put initial conditions. Okay, but there is another method. So this brings us to the boundary conditions. Boundary conditions, which we'll call BC. And here again, it's very similar to the initial condition that we have the problem that the Navier-Stokes boundary conditions cannot be used directly. Again, because we have more information to deal with, yeah, because we have the entire distribution to deal with, which means we have to set boundary conditions for populations. And it's usually easier to think about it this way, that we have to set boundary conditions for populations rather than for moments. Okay. In this world, there are two ways of thought, so to speak, namely the node-based boundary conditions and the link-based boundary conditions. So these guys are sometimes also called wet. It's wet written with one T, I guess. So sorry, my pen doesn't work here. Wet BCs, sometimes they are called wet BCs. So node-based means they put the boundary condition on the node. Yeah. So we'll make use of our characteristic diagram with X and T and nodes being placed here. So this, of course, now looks very one-dimensional. Now here would be the next node, and say we'll put our boundary directly here, so that the boundary is directly on a node. Yeah? And here we have, of course, the population going this way, and this way. So meaning that maybe I go one further here. So we have things so we need these guys, and what we have is this guys. So say this would, for this node here, for the boundary node, this would be a pre-collision at the boundary, so F, and the other one would be a post-collision at the boundary node, so an F star. Okay, even these wet or node-based boundary conditions can be implemented in two different ways. First is we can replace all the populations, so we just say we just know what populations, what distribution we want to have on the boundary, and we just put it there as a Dirichlet boundary condition, right? So replace all distributions on the BC node with something. For example, you could put the equilibrium, or you could do something more clever than that. Or the second method is to only replace what you are missing. So see, this boundary node obviously has neighbors in the fluid domain, so it gets some information from the fluid, right? And you can use this, you can keep this information, the distributions that go out of the domain and inside the boundary node, and complement this information with the information of your boundary condition, and from this you can compute the outgoing distribution. And this is what is usually done in this kind of boundaries. What then happens if you use case number 2 is that the node-based boundaries will obviously depend on the orientation, because the boundaries that, or the populations that go into the boundary from the domain, they are sensitive to the direction in which the boundary is, obviously. And this has as a consequence that these kind of boundary conditions cannot be easily generalized to other cases. So, by the way, they can be easily generalized from a wall, left to a wall right. So you just turn them around. But what you want to have is you want to have an inclined wall or bent wall or something like this, and for them, or you have a corner somewhere, and there it's not easily generalized. And they only exist, therefore, for specific cases. In particular, they exist for straight walls. You can easily put straight walls like this, but what is more complicated than a straight wall is difficult. Okay, so one example I unfortunately have to talk about is an infamous, sorry for these guys, I mean, they just were early comers, so, and her is a very difficult to pronounce name if you're not Chinese. It's not he. I mean, it is a he, it's a guy, I've seen him, yeah, but his name is her or something. Okay, quite some time ago, almost 30 years ago, they invented this guy for the D2Q9 lattice. And I have to warn you, so that this is not something that's really in use. But anyway, it is for didactical purposes. It's very important. You just should remember this as a historical view. It's not working that well, this thing, but it's important to get an understanding on how things here in principle work. So the idea behind this, you write equation 7.1, is that there is given a velocity in x direction, and this velocity in x direction is, sorry, I should probably, okay, before I write this, let me introduce the actual problem that I've skipped over. So say this is our lattice, and we put the wall kind of here, yeah? So when the wall is there, this means that the populations that would come this way are missing. So this means it's before collision, the populations F11, F10, and F1 minus 1, they are unknown. I'm not able to write unknown. Okay, whatever. Unknown. You write it yourself. So now suppose there is a given velocity ux at the boundary, then this velocity obviously can be computed as the sum over I Fij, yeah, and we are omitting delta x and delta t for the time being here. So this means I put the stuff that we are looking for in these brackets, f11 plus f10 plus f1 minus 1, plus the other, minus the other things, f minus 1 minus 1 minus f minus 10 minus f minus 1, 1, right? So this is how we compute the velocity, yeah? Then from this half we know and half we don't know. So then 7.2, we have also given a velocity in the y direction, which we compute as ij, j, fij, and here we'll have the unknown stuff is f11 minus f1 minus 1, and this into f minus 1, 1 plus f01 minus f minus f01. Okay, now you see this happens. By the way, I know that this means we have half time, because this pen only works half a lecture. Okay, so 1, 2, 3, 4, 5, 6, yes. Okay, and then we also assume that there is a given density. Density is just the sum over all of them, ij, fij. So in this we also have the guys that are missing, 1, 0 plus f1 minus 1 and everything else. F minus 1 minus 1 plus f minus 0 plus f01 plus 01 f0 minus 1 plus f00. So I hope these are mine. Okay, so the way of thinking 30 years ago was, okay, so you have three equations, you have three unknowns, so you solve for them, right? Very pretty straightforward. What you observe here is that this guy here appears twice, so we can plug rho just in the definition of velocity, right? So we have 7.1, so everything I'm doing now is just solving the equations for the three unknowns. Gives us 7.4 is rho f minus 1 minus 1 plus f minus 0 plus f minus 0, 1 plus f0 minus 1 plus f0, 0 is equal to ux rho f minus 1 minus 1 plus f minus 1, 0 plus f minus 1, 1. And okay, so there is actually an interdependence between the two, and therefore we'll have one more thing to consider. We now consider the so-called non-equilibrium bounce back. So we say that f10 minus f01 equilibrium, f10, I mean the non-equilibrium of the outgoing distribution, in x direction is the non-equilibrium of the ingoing direction. Okay, so this is an arbitrary assumption that they made. And then what they do is they solve 7.2, 7.4, and 7.5 for f1, 1, f1 minus 1, and f1, 0. Okay, so this is what they did, and the funny thing is this appears in many textbooks, and my observation, even though I'm always telling students in the lecture they should not use this, when I get the homework back, they all say, oh, we implemented Suhe boundary conditions. Or I don't know whether they implemented or they downloaded it somewhere in an example, because most of the examples out there use Suhe boundary conditions. So problems with this, difficult to generalize to other orientations, in particular if there are corners, because at corners you have more conditions, there are more missing distributions. The most important reason why this is not used in practice is it's very unstable. I mean, you can use it, but our tool here is not using it, because what this can done, our toy tool here, what this can done could not be done with Suhe boundary conditions, because Suhe boundary conditions would crash it. So you have to have enough viscosity such that the instability is cancelled out. It is, for historical reasons, popular in textbooks and in small examples that you find in the internet to explain what is lattice Boltzmann. here, unfortunately, you came to me. I'm not somebody talking about simple lattice Boltzmann. We think that lattice Boltzmann is a serious business, yeah, and that there has been development in the last 30 years which makes life much, much better. Stable and more general, and also able to put boundary conditions somewhere else. And this brings us half an hour, yeah. This brings us to the more modern way of thinking, to the link-based boundary conditions. Okay, the link-based boundary conditions, they are not imposed on a node, but they are imposed somewhere in between. And if you think back where I said that the distributions are actually not stored on the link during the collision, but in between the nodes, yeah, then you can already recognize, yeah, it should actually be better to place the boundary condition not directly on the node, but in between the nodes. By the way, this is also done in control volume methods. Yeah, they don't put the boundaries on the node; they put it on the faces. Yeah, so we do something similar here, but our problem is that we cannot move the faces. Yeah, because we are on a lattice. Okay, let's look again on our characteristic diagram. So again, here is x and here is t, and we'll have this. So now I put it this way. So here are the nodes where we have the collisions, and now suppose Okay, suppose here's the end of our domain, and we have a wall directly in between. So what we can do with the distribution going out here, so what a particle would do if it collides with the wall, it would come back. Yeah? So, and this would be here the F star going in, and this is the F pre-collision coming out, so in the opposite direction, in the minus I direction. So in this picture, the boundary condition is positioned halfway between nodes. And this is why it's called halfway bounce back. There are people who don't like this name, but we'll not discuss this now. So, halfway bounce back. This is more or less a mirror for the populations in their flight. The outgoing, the mirror of the outgoing, not distribution, so this is the wrong word, population. In flight. So this will place it directly halfway, and we'll have the new distribution in the direction opposite to the wall at xn, so this here is xn. So this here is time t, and this here is time t plus delta t. At t plus delta t is equal to the outgoing distribution at the same place. So this is I minus, and this is Fi, yeah, the opposite direction, the same location and the previous time. So this way of putting a boundary condition we call bounce back. bounce back, and this is a no-slip boundary condition. So this means that the velocity equals to 0 boundary condition, no penetration and no slip. Okay, this is practically speaking not really the way it is done. Even so, okay, some people do it this way, but this is not necessarily the way that is done. What is more common and more stable, actually, is the so-called delayed bounce back. Some people say this is less accurate, but I kind of disagree, because when something goes unstable, then it's obviously inaccurate, right? Okay, so what is the delayed bounce back doing? We have our diagram again, so this is something we'll make a lot of use here. So it's x and t, and we have our nodes. And let's say here's the wall, and I need one time step more. So instead of, as we just had it, that the population goes out and returns in the next time step, what is happening in a delayed bounce back is that the population actually goes into the wall and returns one time step later from the wall. Yeah? So physically speaking, you would say, okay, there is something, so the other one looks more reasonable, right? Yeah. The reason why this is used is that there is something, so this comes back 2 time steps later, fi asterisk x n and t. Okay, so the reason why this is done just empirically, and this can also be explained, but the explanation is a little bit complicated, is that this way of doing the bounce back is much more stable than the other one. And this has to do with high frequency oscillations. Yeah? So this guy here will cancel high frequency oscillations, while the other one will amplify high frequency oscillations, and this makes it unstable, while this here is stable. Yeah? So this is why we use the delay. This is more stable. By the way, this is something that I guess this is not written in textbooks, and also the literature does not talk a lot about this, because this, I don't know, it looks strange and doesn't seem to be a good advertisement for the lattice Boltzmann method. So this is something that practitioners know, yeah, and is not necessarily. So if you deal with the method a lot, then you would know that, but it's not discussed that in the literature usually. Okay. Now this only gives us no-slip boundary conditions. What we are also interested in is velocity boundary conditions, and for this we put velocity bounce back. There's also pressure boundary conditions, but we'll not come to this here, unfortunately, because of time. So we can generalize the bounce back boundary conditions, both of them, no matter whether we use the delayed or the non-delayed version, to a non-zero velocity. I'm now not going through the derivation of this. I'm just giving it to you because I want to go to something else and need some time for this too. So I'll just say, so So now this is the non-delayed version, but we can also write it as the delayed version. So the new population here is equal to the previous population going out and t. So this would be the usual bounce back. Yeah? And then in order to give a velocity on top of this, we just add the momentum. Yeah? We just add it and we do it. There's a 2 here related because the guy that's going out, we have to subtract their velocity. So we have to subtract the velocity that's going out and add it again, so in order to reverse it. So this is why there's a 2. There is this 1/3 theta, and there is the weight of the link we are talking about, and then there's a direction, there's the velocity component of that particular link. So the link is I, yeah, so the vector, the unit vector here, or no, the directional vector is not necessarily a unit vector, but the vector of the link is EI times the velocity, yeah, scalar product, and this weighted by this omega, that not by the omega, by the W. So this here is 1/3, and these here are the lattice weights. They depend on what lattice you have, but they are the same as in the BGK collision operator. Yeah, in the BGK collision operator we also use these weights, and they are the same here. Okay, so the reason why I'm not spending too much time on this, and I just see that I have to speed up a little bit, is because I want to go to something that is important for the actual practice of the Lattice-Boltzmann method, namely the off-lattice boundary conditions, which we call also ways out of Lego land. So the problem, one fundamental problem of Lattice-Boltzmann is we are using Cartesian grids. And now you could say, well, the world is not Cartesian, so how would I put my objects into it? So one way you can do it, you can always use staircase approximation. Yeah? But this is not very accurate. This is what we have in our toy here. That is a staircase approximation. However, it is possible to put boundary conditions at locations that are off lattice, and this is done by interpolation. So the first one doing this, so it would lead us to interpolated bounce back. So there are several methods. The first of which comes from a guy called Bosidi and also his colleagues. It's kind of 20 years ago. So his idea was to introduce a subgrid distance as a measure of where the boundary actually is. And he calls the subgrid distance Q. So Q is the fraction of AE delta X between the last grid node and the boundary, or the wall, say the wall. So which means that 0 is equal to Q and this. So Q goes from 0 to 1, basically. Yeah. So it's either here or it's there or somewhere in between. Okay. So what Bosidi did is he looked at two different cases, and for this, we again draw our characteristic diagram. By the way, 20 years ago, the characteristic diagram for the Lattice-Boltzmann method was not yet invented. So the pictures from Bossidi look pretty different from what I'm drawing here, but we'll stick to our modern view. So here again we have x and here we have t, and we'll have our nodes. And now let me see. Yes, so what he did, he distinguished two cases, namely the one where q is smaller than 1/2 and where q is either 1/2 or larger than 1. What am I writing? Where q is larger than 1/2. Okay, let's start with the condition q is smaller than 1/2. Means I put my boundary here. Okay? Because this distance is q delta x. So what he then said was that what he wants to have is the population that is coming in here, and this would come from the wall, and here would be the bounce back, so it would come actually from this location, right? So the idea now is that he has to obtain the population at this location here. And for this he has to do an interpolation before the collision. Now this is moving q and q back, and the entire distance it's moving is 1, or delta x. Yeah? So the entire distance here covered is delta x minus 2 delta x q, yeah, because it's going the way q twice, right? So this is the distance covered here, which means that at the location xn, now this is the location xn minus delta x. This is minus delta x, and that's right, delta x. Sorry for not having the right pen. And here would be, this location here would be xn, where we want to put our boundary condition. Now, because this distance here is delta x minus 2 delta xq, this means that this here must be 2q delta x. And he's doing the interpolation between this thing here. So we're using linear interpolation. Fi, the opposite way, xn t in the next time step is equal to linearly interpolated 2q, the post-collision state of what is going out here. So this is the, what is this called? The leverage law, or the linear interpolation. So you use this distance here, 2q delta x times the one on the right, plus the opposite 1 minus 2q, sorry. It's always difficult to remove this. 1 minus 2q times the guy from the neighbor, so the neighboring guy, so this is fi star xn minus delta x. Okay, so so here I write, so if we are in more than one dimension, it's not just I delta x is also the vector, of course, yeah? So what direction we are coming from. Okay, so this is one case, and the other case is that Q is larger or equal to 0.5. Then we have to do this differently. Means we draw a new diagram. So larger than 1/2. Say this is inside the wall. So we set Q x and t. So this here is delta x times Q, and this is obviously larger than 1/2, right? So in this case, what is happening is the population comes here. Should draw this correctly. Here is difficult to remove something with this pen. So it will come here will be reflected, and then it ends up here. So it will not reach this. But we also have the guide that is going this way. So this here is now delta x, and this distance here that's left here is now actually delta x minus what we had before, 1 minus this distance here, this is 2q minus 1. So it's kind of the opposite to what we had here previously. So the entire distance that we cover, okay, maybe I should put delta x to make it the distance actually. So the entire distance that we cover is delta x plus delta x, or 2q delta x minus delta x. So we'll have the entire distance covered is then 2q delta x. So the interpolation between these guys looks like this. Is 1 over 2q fi asterisk xn and t plus 2q minus 1 divided by 2q f. Now the one going in the opposite direction in xn and t. So kind of what is beautiful about this is that it's only dependent on the populations on the same node, right? So we don't need to know anything from our neighbor for this case. However, this is not general, because in the other case, we need to know something about our neighbor. Now, the last 10 minutes, we look at an even more modern way of doing this, using so-called one-point interpolation, where we do not require any neighbor, but we can do everything locally. Now this is kind of funny because we actually do an interpolation, but for doing an interpolation we use only 1 point. How is this possible? It's possible due to moments. Okay, now the picture is the following. Here is t, here is x. and here are located the nodes. This would be outside, and somewhere in between, where we don't care whether it's larger or smaller, is the wall. Yeah. So this again here is delta x times q. Okay. Now, what Busidi did was all related to interpolation inside space and not inside time. What we do instead here is we use a linear interpolation along the characteristic, which we can easily do in our picture here. So what does this mean? The characteristic is the trace that our particle is taking. Yeah? So the particle is going to here, and then it will reflect, and so in here in this position it will be reflected. And sorry, let me draw this again. So on the other side we have a particle that's going here. Now, instead of trying to do an interpolation only in space, we do an interpolation in space and time. Yeah, so basically we are connecting these 2 points. Yeah, and what we can say is that this here is delta xq, and also this is delta tq, right? And now what we want to do is we want to interpolate. So we know these things here, or we can find out what these things here, and we want to interpolate to this position, to the right position in space, where this here is xn. And we are going to call this point here xa. Okay, let's go first to what is happening here on the boundary. Here we have Fi is xbc, so this here is xbc, the location of the boundary. Then we will arrive there at t plus q delta t, yeah, because now we are also interpolating in time. This would be Fi xn. So the pre-collision state up here, and this here, say this down here, this will be our virtual node. Yeah, so here we have a virtual position inside the wall. So the pre-collision state here, then we have to do an interpolation, 1 minus q coming there, plus Fi at the virtual position, and t at the later time step. So this would be the distribution, this would be the population down here, yeah, and the other one up here. And this is weighted with q. Now, the important thing is we know what this is, because the pre-collision state inside the wall at a later time step obviously is the post-collision distribution at the node before the wall at the current time step, right? Pretty simple. So we can do this replacement. And this leads us to our equation that I called 1 now. So this is the Fi, so the distribution at the boundary. the location of the boundary, at time t plus q delta t is equal to fi x n t 1 minus q plus the post-collision state of the same, at the same position. And this times q. Yeah? So all the local, just, this is interpolation in one point, because we distinguish between the pre and the post-collision state. Yeah? Okay, what happens on the wall is a bounce back. So on the wall we have a bounce back. Which means that the distribution on the wall, going in the opposite direction, BC, at t plus q delta t is just the same thing as the above. T is 1 minus q plus post-collision ix in t multiplied by q. So, but this is not what we want to know. We want to know the distribution at the next time step at xn. This is what we want to know. So, what is fi in the opposite direction, missing direction fi over bar, or fi minus, at xn? So this is the question. So sorry for going back, but you're not writing anyway. So what we simply do, we interpolate between these two positions. Yeah, and we don't mind for the time being that is not straight, but it's going, in space and time at the same time, right? So we do the interpolation. Interpolation between this fi at the neighboring node, which I call A here, at the next time step, delta t, and the one that we know, fi over bar x bc t plus q delta t. So doing this, okay, we are running a little bit out of time. I give you the result. Hope I noticed, though, if you have watched this video from last year, then there was a mistake here, and I hope now I've corrected it. So if we do the interpolation, we'll end up with, okay, so of course it's your homework to check whether it's now correct and what was the mistake last year. So I write it without derivations. We just do the interpolation between these 2 points, and what comes out is q by q plus 1. Plus, not written this here, plus the thing at the boundary, xbc. So if I don't find my pen, I have a big problem. xbc t plus q delta t times 1 over q plus 1. Now you see in time, when you look at the timing of the two things, then this is q delta t times 1 over q delta t, and here is delta t times q plus 1. So this is why both of them come at the same location in time. And now, again, we have something at the neighboring node, but what we have at the neighboring node, so that's the same thing that we had in the Bosidi boundary condition. for the second case, we can just replace this as the post-collision population at the node itself. And with this, we plug in our equation number 1 and we get Fixn t plus 2q delta t q plus 1 is equal to q divided by q plus 1 f minus I xn t plus f I xn and t times 1 minus q divided by q. That's not a g, that's a q. Q plus 1 plus fi post-collision xn t and q by q plus 1. So everything is just dependent on the node itself where we want to put the boundary condition. The only problem that we still have is this guy here. Yeah, it's not plus delta x, it's plus 2q by q plus 1 delta x. So what are we going to do with this? We are just going to ignore this because in diffusive scaling, an error of delta t would be proportional to epsilon 2, right? So the error that we do here is the same error that we have already from the linear interpolation in space. So we can use constant interpolation in time. It's the same accuracy as linear interpolation in space. Since we use only linear interpolation in space, there is no point to be more accurate than constant in time. And this is also the reason why the delay bounce back works. Yeah? In the delay bounce back, we are also doing a constant interpolation in time, and it has almost no effect other than it makes it more stable. Yeah? So there's a little error on this, so this is accurate enough. And we say the errors in time are not important. And we say that this 2q plus 1 delta t is then replaced by delta t, and this leads us, sorry for taking 5 minutes more, into the boundary condition xn t plus delta t. We are going low again, is equal to fi xn t q divided by q plus 1 plus fi xn t 1 minus q divided by q plus 1 plus fi after collision xn. So it's all the same xn, it's all the same time, q divided by q plus 1. So now this is the one-point boundary condition that allows you to place your boundary any place in between the nodes. So you're not restricted to Cartesian boundary conditions in the Lattice-Boltzmann method anymore, and this only uses local information in space and time. Thank you for attending.